And let the games begin. All right. So does anybody remember what we talked about last week? Hi, Sal.
You said you were going to do a problem that takes up all of the way.
Which is why I'm moving my camera.
Scoot more in if you need to.
Just trying to bump this, please. And don't chew on it. Come on, Trace.
I'll try not to.
Okay, thank you. Does anybody remember what we talked about last week? We talked about inductance. We talked about capacitance. And we really only put them in circuits by themselves. We took a few cases where we made some graphs. It was fun. We had some laughs. We had some good times. We had some bad times. And all those other times in between. So, yeah. This week, we're moving into Chapter 4. I don't remember what the chapter is called. But Chapter 4 is higher order systems. Okay. So we're just going to jump right into this because we're bold, we're fierce, we're brave. What I have just drawn on the board is something you will come to loathe. They are not components we haven't seen before in this class. However, math behind it is atrocious. I'm going to give some values to this just so that we can make it solvable. This will be our VS value. We'll go ahead and make this 10 volts. Sure, why not? This will be our resistance value. We'll go ahead and make this 1,000 ohms. And this will be our capacitance value. Bless you. Somebody's allergic to math. This will be our capacitance value. And we will make this be equal to 1 millifarad. Why not? How do we solve this? Well, does anybody remember the 3 equation sets that I gave you last class? I actually wrote out equation set 1, equation set 2, equation set 3. Anybody remember what those are? That was not one of them, no. Although power is, I mean, that is an equation that we use throughout class.
Would be like I equals C, dv over dt.
That was one of the equation sets. I wrote out 3 equation sets on the board. Those 3 equation sets are used to solve every single electronics problem.
V equals IL di over dt. Or V equals L di over dt.
That was one of the equation sets. What was the other ones? Okay, well, I'll just give them to you rather than draw this out. Huh?
Oh, VL equals L dil over dt.
That was one of them. In every problem, you have 3 equation sets. The first one is KVL. What is KVL? What's that?
Sum of the volts in equals sum of the volts out.
Yep. Inside of a loop, the sum of the voltages is equal to 0. Or voltages that come in is equal to voltages that come out. The amount of energy that's put into the system is equal to the amount of energy that comes out of the system. Okay, how many loops do we have in this system right here? We have 1. So what is our KVL equation set, which is only going to have 1 equation? What is it? Well, here, we don't have an inductance in here. But we do have a resistance and a capacitance. So, VR1 plus VC1. That is our equation set number 1. Which makes sense. I mean, the amount of voltage in the source is equal to the amount of voltages in the rest of the system. Okay, so this, I'm just going to go ahead and box it. That's equation set 1. We did KVL. Okay? Anybody know what equation set 2 is going to be? KCL. They're like best friends. They always show up in the same places together. Okay? What equations do we have for KCL? Right, current in equals current out. It's like KVL, just with a node instead of a loop. So at node 1, what is the current coming into node 1? It's IS, yeah. This funny little switch here just means that it's like a button and the button is being pressed and held at time equals 0. Which means we can consider it to be a wire at time equals 0, and beyond that, nothing. So at 1, the current coming in is going to be equals to IS. So IS is equal to what? What's the current coming out of 1? It goes through the switch and it goes into what? What? I heard somebody say it. It goes into the resistor. So IS is equal to IR1. Okay, what about node 2? What is our equation at node 2? What current goes into node 2? The resistor. So IR1 is equal to, what is the current going out of node 2? IC1. I'm glad you saw it too. I won't put that in my comedy routine. All right, you know what, just for fun, let's do node 3 too. What is the current going into node 3? It's IC1. What is the current going out of node 3? It's IS. Okay, all of the current that's coming out of the capacitor goes through node 3 and into the negative terminal of the battery. So this is our equation set number 2. Which I then boxed. And now it's time for me to move the camera again. All right, so we have 2 of our equation sets. Anybody have a guess on what the third equation set is? You mentioned an equation. I said it was one of them. It's not up here on the board yet. What is it? What did you say?
That's the 3 of them. The VL equals L, DIL over dt.
Okay. That was one of the ones you said, yes?
V equals IL, di over dt, or V equals L, di over dt.
Yeah, that's the same equation.
Yep, and then I equals C dV over dt.
I C equals C dVc dt. Okay, and then we have one other equation. Both of these equations, what they do is they link voltage and current. We have one other equation that links voltage and current that we haven't written down yet. Probably write those bigger. That's true in a capacitor, yes. That is a capacitor equation, but it's an equation that has voltage and current in it. You guys knew it before you came to class. Huh? V equals IR. So, equation set 3. We know our individual component equations. Okay, this is the relationship between voltage and current inside of each one of these components. Here we have a resistor, which means we're going to need Ohm's law. VR1 is equal to IR1 times R1. Ohm's law. Okay, this relationship is true because we know that's how a resistor works. The second equation is one that Trace just gave me. IC1 is equal to C1 times d VC1 dt. If we had an inductor, that third one would work too. In this system, we don't have an inductor. But when we do have a system with an inductor with it, we will write that in here, okay? I'm going to go ahead and box this because this is equation set 3. Now, for every single circuit system we solve, you will always have those 3 equation sets. Equation set 1, KVL. Equation set 2, KCL. Remember, this one is the law of conservation of energy. Energy in has to equal energy out. That has to be true for every physical system. It's a physical constraint on every system. This is KCL. Hey, Dylan.
Hey.
KCL is a derivation of the law of conservation of mass. Mass in the system does not change. And then the third one, relationship components, the relationships between different components, resistance, capacitance, inductance. It's the relationship between voltage and current. Okay? We will always have these same 3 equation sets for every problem. And you're going to really need to know that starting this week. Okay, so we have some fun stuff. What do we do with it? Well, I'm going to solve for the voltage on the capacitor. Okay, so overall, we're just looking for what is VC1. Okay. So to start that process, usually what we do is we take equation set 1, 2, and 3 and we just start mixing them together. We have enough equations, we might as well play with them. So I'm going to start with this one. The reason why I'm starting with this one is because this contains Vs, which we know, and VC1, which we want to know. It just makes sense. So I'll write that again over here. Vs is equal to VR1 plus VC1. Nothing groundbreaking yet. It's just KVL. Now I'm going to bring in equation set number 3. So I'll write equation set 3. Using equation set 3, what can I do with VR1? I can substitute it. What does it become? Yep, IR1 times R1 plus VC1. Okay? Now I'm going to use equation set 2. What is special about equation set 2? Where can I use that in the equation? I can change the IR1 value. If I change IR1, I can actually change it to IC1, which we're getting one step closer to being able to define that in terms of VC. So, using equation set 2, Vs is equal to IC1 R1 plus VC1, because these two are equal. That's this equation right here. IR1 equals IC1. One last step. I'm going to go back and I'm going to use equation set number 3. And when I use equation set number 3, I'm going to replace IC1 with IC equals C dVc dt. So Vs is equal to C1 dVc1 dt times R1 plus Vc1. Now, I have one unknown in this equation. It's Vc1. I have a known value. I got my unknown value. One equation, one known, one unknown. Solvable, right? For all of you who have already taken Calc 2, this is where your eyes go big and you go, oh, heck no. Not again. Haven't you haunted me enough, O calculus? How do we solve that? There's a number of ways. You can use a Laplace transform. Laplace transforms work. Laplace transforms would be a very simple way of solving this. Just plug it in, do some algebra, regurgitate an answer. Okay. I like to teach it a little bit different when I do it. Because at the end of the day, one of the things I like about both math and engineering is that we can look forward to the end of the problem, and say, I think I know what this is going to look like. Okay? For this problem, we are adding a function to a derivative of the function to get it to be equal to a constant. Believe it or not, that gives us some opportunities. A function plus its own derivative have to add to something unique. So, a function plus its derivative is equal to a constant. Well, that's interesting. All right, let's play with this idea for a little bit. It's part of the reason why this equation takes up the entire board. Okay, I have a function x of t. I do not know what that x of t is. Okay, but I know that it's equal to 5. Which is kind of funny because that means you know exactly what it is. Okay, what is the time? How does this function change with time? It doesn't. It can't. If x has any, I mean, when you write out x as a function of t, you're like t to the first, well, you have to have a coefficient of 0 in front of that. Plus t to the second, well, you have to have a coefficient of 0 in front of that too. Cosine of t, you have to have a coefficient of 0 in front of that too, because it can't change with time. It always has to be 5. And there's no way of adding t plus t squared and always equaling 5. At some time t, you might be able to equal 5, but there's no way to have a coefficient set where any of these can add to 5. What you end up with is 5 t to the 0th always. That's what it has to be. When it comes down to it, we have to have what's called the same time functions on both sides of our equation. And what that means is everything over here that is not equal to a constant has to sum to 0. Everything over here is a constant. Okay? We have to have the same time functions on both sides. It doesn't make sense if we have different time functions on both sides. If one side, if you know that the function x of t has a t in it, you're also going to know that the coefficients are going to have to sum to 0. Okay? If this is x of t plus y of t are equal to 5, where now both x and y of t have some other components to them. Everything that is not a constant has to cancel out, right? If x is equal to a times cosine of t, if that's what x of 5 is equal to, what is y of 5 going to be equal to? What is y of t? Y of t is equal to negative a cosine t plus 5, or 5 minus, whatever. You can rearrange that, right? We know this. Look at this, though. This negative a cosine t adds to a cosine t to equal 0. It has to. There's no other way. Because there's a 0 on this side. And what you can end up doing with this equation is you can actually break this out into multiple pieces. Okay? So we can take a cosine of t minus a cosine of t is equal to 0, and then we can take 0 plus 5 is equal to 5. And what y is a sum of these two, and what x is the sum of these two, and what the end resultant is the sum of these two. I just broke out the equation. Now this has the same time function. All of these are cosines. These have the same time functions. All of them are constants. Nothing groundbreaking, right? Hopefully. I hope this is fairly elementary. I'm like spoon feeding you. All of this has a conclusion to it. Everything has to have the same time functions. You have to. One side time function has to equal another side time function. And unless you're looking at a very specific incident where two time functions cross, if you're trying to make two functions equal to each other, they have to be equal at all times t, which is what we have here. They must be equal at all times t. There cannot be a time t where they do not equal each other, which is why their time functions have to sum to 0. This would be a lot harder if we say at t equals 5. Then it equals 5. Because then I have to give you more information. Because then you only know one single point on what that function is going to be. They don't have to be equal to each other anymore. But if I'm giving you a function is equal to another function, the functions have to have the same time function. Have to. Okay? So now we go back and look at this idea. A function plus its derivative is equal to a constant. That implies two things. Implication number one, the function is a constant. If the function is a constant, its own derivative is 0. Right? We can solve this problem if v of c is equal to 5. Or 10, sorry. Right? Done. If we say v of c is equal to 10, this equation right here, it means its own derivative is equal to 0, and then its 10 is equal to 10. Is that true for all times t? Yes, it works. Oh, we're done. Well, not really. But that's one train of thought. One answer to this solution is Vc is equal to a constant. Because if we do that, we have the same time function on both sides. We're done. By the way, that's a steady state solution. If Vc is a constant, we know what the answer is. Vc at some point is going to be equal to 10. And it's steady state because at that point, the derivative is equal to 0. There's no change in the system. So yeah, I'm just getting ahead of myself there. So I just get so excited about math. Ugh, bristling. Okay, so that's one of our two implications, is that the function is a constant. If the function is a constant, function plus derivative equals constant, check. But there's a second implication, because math is never straightforward. And that second implication is the function added to its derivative is equal to 0 plus a constant. Which means that the time function of the derivative is equal to the time function of the function itself. Hey, Gabby.
Hi.
Oh man, I'm gonna have to move my camera again. Do we know of any functions that when you take the derivative looks like itself? Huh? Yes. Well, that was fast. Usually people wait to give me that answer. What?
I was just waiting to say it all morning.
Because what?
I was just waiting to say it all morning. I had E to the X on my mind.
How did you know? At least you share my enthusiasm. Okay, there is a function, actually there's three functions that if you take their derivatives are equal to each other, okay? But that function, well, ironically, if you use Euler's equation, they're all one formula. But we'll talk about that another time. E to the t. If I take some value a1 e to the t. And I take the derivative of that, d dt of a1 e to the t. What is the derivative of this function? A1 e to the t. I feel like I gave you the answer. Yeah, but you're right. That's what it is. That is its own derivative. And guess what? If we add those together, we can get 0, assuming that one of them is negative. So all we would need to do is we would need to put a negative sign up here. What happens when we take the derivative of this now? It becomes negative a1 e to the t. If we add this one and this one together, we get 0. Done. That's the second implication. The function added to its derivative is equal to 0. Now here, if we go back and look at our equation, Vs is equal to C1 dVc1 dt times R1 plus Vc. Well, we have to multiply it by a constant first. So we know that, well, I'm going to write this out in a little bit more general. A1 e to the negative st. That's going to be our function. Okay? And then when we take the derivative of it, d dt, and then we multiply the derivative of it by C1 R1, we know that this is going to be equal to negative a1 e to the negative st. Everybody see how I did that? Here, this is dVc1 dt times R1 C1, and this is Vc1. Now, I'm ignoring the constants. Because like I did earlier, turns out we can break this up. Here, y of t was equal to a cosine of t plus 5. X of t was a cosine t plus 0. And the final solution was 0 plus 5. That's how we did it. We're just going to focus on this part that equals 0 right now, which is called the homogeneous equation. I had to give you the stink eye for a little bit. Just waiting for you to like jump in and be like, I know the answer. Okay, thank you. This is what we're looking at right now is called the homogeneous equation. Okay. Okay, also known as the it's the, I don't know, it's the C equation. Homogeneous as the same as, oh, I forgot the term. There's a particular solution and there's a, what? General solution, but it starts with a C. But you're right, that is the term. Dang it, that's going to bother me. Complementary, that's it. Okay. Have you been waiting to say that all day too? Okay.
As soon as you said it started with C.
Well, thank you for that, because that was going to bother me. This is our homogeneous equation, which is our complementary solution. Okay, here, this is the complementary solution to y of t. It's the part that sums to 0. So this is where I should be like this to the camera. Okay. So what we've come up with here is this is our complementary solution. This up here is the complementary solution to y of t. This is what's known as the particular solution of y of t. That's basically what we're doing, okay? We know that some function plus itself has to equal to 0. We know that that function takes the form of a1 e to the st. And this is now solvable. It has to be true. It has to be equal to the negative of itself. So here, I mean, all we need to do here is just friggin' take a derivative. To which now I'm going to point the camera that way and I'm going to teach behind you. Working all the way around. If I can get to that board, I'll be happy. Just ignore the fact that you're on camera. If you want to move to a different seat, you can. Just had a weird zoom in moment. Okay. Starting new with a fresh board. Okay, so we know what the end solution is going to be. VC is equal to VC complementary plus VC particular. Okay? Y of t complementary, Y of t particular. VC complementary, and then the VC particular is going to sum to 5. Which is hilarious, but whatever. Okay, we know this is the solution. Complementary plus particular. Right underneath this is complementary. You're so nice. But this one's a little weird. It's pretty particular. This is why I relate to math so much. Okay? To find the complementary solution, we ignore the forcing function. And we set everything else equal to 0. When we do that, what we end up with is this right here, where a function added to its derivative equals 0 plus some kind of a constant, where the c is the constant, is the particular solution, which we will ignore for now. Okay, we'll start with complementary. Okay, if we plug in our complementary solution, we know it's probably going to take the form of VCC is equal to A1e to the ST. Right? I wrote that up there on purpose. Okay, so if we take our complementary solution, we plug it in to our original equation, which we have over here. That's this one, which I will write over there on the board again. If we plug it in, we should be able to get 0 as long as we make Vs equal to 0. The idea of complementary. 0 is equal to R1 C1 times d VCC dt dVC1C dt plus VC1C. I just write the C behind it to make it the complementary piece. Right? All I did was I just took this equation and I replaced VC1 with VC1 comma C, and then I changed Vs equal to 0. Okay? I turned it into the homogeneous equation. Because all we're solving for here is we're not solving for this equals to a constant. We're solving for this, these functions cancel out. We're solving for that second implication. Function added to its derivative is equal to 0. Okay? So, in doing this, we already have our estimate of the solution. It's, as Jonathan pointed out, it's A1e to the ST. All we have to do is plug that in. So, 0 is equal to R1 C1 times d dt of A1e to the ST plus A1e to the ST. No major jumps yet. Just plugging things in. I guess actually this right here is the major jump. We know what the end solution is. We're solving it using differential equations. What is the derivative of A1e to the ST? Yes. So this becomes 0 equals R1 C1 A1 E to the ST plus A1 E to the ST. We can take both sides and divide out A1 E to the ST. Right? Because A1 e to the ST shows up in both places. A1 e to the ST, divide the left side by A1 e to the ST. And then what we get is what's left over. 0 is equal to R1 C1 S plus 1. Look, no time. There's no functions anymore. We're dealing with constants again. But now we can't solve for A1. But we can solve for S. So we bring this over and R1 C1 S is equal to -1. S is equal to -1 over R1 C1. Nice.
Wouldn't it be a positive?
No.
What is that?
Because this is R1C1S plus 1. When we take 1 to the other side, it becomes a negative 1. And as I pointed out earlier, this is probably going to have to be negative, because then this is a1e to the t negative t, and then it's a1e to the negative t, and they sum. These can sum together, and that's, they cancel out that way. So actually having a negative in the exponent is necessary. But I like that you have an inquisitive mind. All right, so we've solved for S. What S is called is, this is effectively called the time constant, okay? We're gonna call 1 over S is equal to the time constant. It's just a definition of the letter tau, okay? I'm not gonna show you why yet, but I'm just gonna throw that out there right now. What this is related to is how quickly the function changes. Because this is multiplied directly by t, this is just how quickly this function is going to reach equilibrium. That's why it's called a time constant, okay? But we'll get into what tau is later. I'm just introducing it right now. So here, for this function, tau is equal to, negative 1 over S is equal to tau, which means that tau is equal to R1C1. Okay? Not that you need to know that right now. It doesn't help you solve the problem at all. It's just weird definitions that your professor's just throwing at you. I am now going to define the function which is, I don't know, I'll make up something. Doesn't make any sense. Now, the problem is, we have no real way of solving for A1 yet. Not yet. Because, I mean, if you just plug it back into here, you're still not going to be able to get A1. Even if you go back and plug it into the particular solution, which is where it equals to 5, you're still not going to be able to solve for A1 yet. But we'll get there. We will get there in time. Okay? We're going to go ahead and guess our particular solution now. Let me make sure my camera is actually pointed at me. Probably turn this. You can see it. Actually tune into myself on YouTube to see if I show up. I've done that before. I'm all the way over to here. Okay, so now we're going to do the particular solution. For the particular solution, the idea behind the particular solution is that you want the particular solution to have the same time function as your forcing function. This is called the forcing function because it's on the other side of the equation. More definitions. Okay? What is the time function of Vs? Is it a cosine function? Tangent function? What kind of function is Vs? It's a constant. Because it's a constant, we're going to expect that our particular solution is going to have the same time function, right? If we go back to y of t over here, the particular solution was 5 because it has the same constant value as the end solution. Samesies. Okay, so we're going to guess VC1 particular is equal to a constant, which I'm going to call A2. Problem is I like using the letter C, but we're already using C. We are very close to being finished. This problem has only taken almost an hour. In fact, at this point it has taken an hour, so we're almost finished. We're going to guess that the particular solution is equal to A2, right? So our second step is we plug this into the non-homogeneous equation, which is a funny way of just saying original at this point. Okay, so what I'm going to do is I'm going to say, okay, our original equation is Vs is equal to R1C1 dVC1 dt plus Vc1, right? That's the original flavor of this equation. It's not that spicy new flavor that we added. Ugh. Now what I'm going to do is I'm going to say, well, this has to be true for the particular solution. I'm going to replace Vc1 with Vc1p. Vs is equal to R1C1 dVc1p dt plus Vc1p. Not a huge change. I just put a comma p after a couple letters. Okay? We know that Vc1p is a constant. So Vs is equal to R1C1 d dt of Vc1p, which is A2, plus A2. What is this derivative? What's the derivative of a constant? It's 0, which means this piece goes away. And what we're left with is that. And what that means is we know the particular solution. We know half of the complementary solution. We know what S is. We know what the particular solution is. We know what A2 is. It's equal to Vs. The only thing we don't know now is A1. And there's only one way we are going to be able to solve for it. Okay? And the only way we can solve for it is something called an initial condition. We have to know at some time t what the value is of the voltage on that capacitor. At any time t, if we know what that value is, we plug it into the equation, we solved it. Okay, what we're going to go ahead and assume is that because if we go back to our original circuit, we flip the switch at t equals 0 to plug in the system. We're going to go ahead and assume that at t equals 0, there were no charges in the capacitor. We're just going to assume that that Vc1 was equal to 0 at t equals 0. And this should have been given to you. I didn't, but I should have given it to you. It's important. You have to know it. Assume Vc1 at 0 is equal to 0. We can go back and plug that into this equation, which we know is the solution. Vc1 is equal to Vc1c plus Vc1p, complementary plus particular. Okay? Vc1 is equal to complementary solution we wrote out as A1 e to the st. Particular solution we wrote out as A2, which we know is Vs. We know what S is because it is our time variable. And now we know that Vc1 at 0 is going to be equal to 0. So we set 0 equal to this equation. We set t equals to 0. A1 e to the s times 0 plus A2. What is e to the 0? It's 1. Which means this equation becomes 0 is equal to A1 plus A2. What is A1? It's a kind of steak sauce. Come on. Jonathan, you're supposed to be on this. Oh, I know, right? You're not even bringing up your steak sauce references? Come on, man. Zero is equal to A1 plus A2. Well, that just means A1 is equal to negative A2. We now know the final solution because we've solved for everything. Go back to this one. Vc1 is equal to negative A2 is equal to negative Vs. Negative Vs. E to the s is equal to negative t over R1C1 plus Vs. That is the solution. I have many regrets. But we did it. We solved for it. And I know that it's fun to be done, but I also like to sit back and think, okay, we derived this really fun equation. It has fun letters in it. It took a lot of really fun steps to get here. Let's talk about what we did. So, let's start back at the beginning. In song form. So originally we had a circuit. We then derived 3 equation sets. We then came up with oh dang. We came up with an equation. Vs equals C1 dVc dt times R1 plus Vc1. We then did a lot of thought experiments. And then we came over here and we're like, okay, I know what the end solution is going to be. It's a complementary plus a particular solution. I prefer to do all of that stupid things off camera, but thank you for thinking of me. I posted that to YouTube. We then came up with what we knew was going to be the end solution is going to be a complementary and a particular solution added together. We solved for S using the complementary solution using the homogeneous equation. Okay? We then solved for A2 because the particular solution, we just used the non-homogeneous equation. We then solved for A1 using initial conditions. Okay? So if I were to write out the steps to solving this problem, 1, draw a circuit. 2, get 3 equation sets. And that's going to be your KVL, KCL, and then component equations. That's what your 3 equation sets are. Third step, find final solution. And this is final solution is equal to complementary plus particular. Okay, step 4 is find your time function. And here you have to use the homogeneous equation. Step 5, find particular solution. And here you have to use non-homogeneous equation. And then step 6, you solve for the final variable using the initial conditions. Rather than find initial conditions, I should say solve. Because initial conditions should be given to you. 6 steps. Does this point at that? I want to make sure that I zoom in on that part. That's what we did. And you know what? When we come back from break, I'm going to give you a harder one. We're going to follow these exact 6 steps. And we'll get the answer again. And we're going to do the same thing again. When it comes to second order systems, this is called a first order system. The reason why it's called a first order system is because it has 1 derivative in it. Second order systems have 2 derivatives. And they become a little bit more complicated. Before I let you leave for break, I am going to use one more whiteboard. But instead of crawling behind you, Gabby, and writing on that one, I'm just going to erase this part and use this one again. I almost made it there. There weren't like 10 frigging million chairs. Next time, I'll go all the way around the room. Okay, I want to plot out what this looks like. Why do I want to plot out what it looks like? I don't know. Don't ask those questions. First of all, I'm going to plot out VS with T. What is VS? What does its graph look like? It's pretty friggin' constant. At 10 volts. Doesn't change. Okay? Now we know that at all times t, our voltage across our capacitor has to add to our voltage across our resistor. What we solved for was VC. So we can actually solve for VR by just taking VS minus VC. Okay, so let's go ahead and plot out what VC looks like. Well, we know VS is equal to 10. We know R1, C1. Well, it's equal to something. It's going to be an exponential function, but it's going to experience exponential decay because this is a negative. So it's going to have a nominal value of 10 volts. At t equals 0, I mean, we force the VC has to equal 0 at t equals 0. So it's going to start at 0, and then it's going to exponentially move towards VS. And that's what it looks like. If you just plug that into your graphing calculator, that's exactly what you would get, is that curve. Okay? So, if we were to take Vs minus Vc, we get Vr. Right? Which means we have our nominal value of Vs. Because this starts at 0, what does Vr have to start at? What is Vr? Vr1 at 0. What is Vc at 0? What is Vs at 0? So what does Vr have to be at 0? It has to be 10. So it has to start at Vs. And what it's going to end up doing is exponentially decaying to 0. I told you at the very beginning of this problem, we had two implications. One of them is, if the function is a constant, the system is stable. Okay? At very, very large values of t, Vc is equal to Vs. And Vr is equal to 0. Our two implications came true in the same equation. It's like they're growing up. I'm going to do one more thing. I'm going to plot the value of IC. When I plot IC, our current through our capacitor, I am also plotting the current that's coming out of the source voltage, and I'm plotting the current that's going through the resistor. One thing you know about the current going through the resistor is that it has the same shape of the function as the voltage across the resistor. It's because they have to. You cannot have a voltage in a resistor without a current. So their time functions are going to be identical, thanks to Ohm's law. So we actually already know what the shape of that curve is. But yeah, just for poops and giggles, we know that IC is equal to C dVc dt. So if we multiply this by C and we take the derivative of this function, we will get IC. So it starts out pretty big, pretty positive, and as we get closer, the derivative gets closer and closer to 0. So it looks like this, which we already knew it looked like that because it is the same time function as the voltage across the resistance. So that's two different ways. If you can solve for IC using Vc, you can then multiply by the resistance and get Vr. Or you can just subtract from Vs and get Vr. A couple different ways you can solve that one. Okay? Now, the important thing to note here is if I make S very, very large, what's going to happen to this curve? Well, I guess before we deal with that, if I make Vs very, very large, what's going to happen to this curve? What's going to happen to this one right here? That equation is true regardless of what Vs is. What happens when I make Vs very large?
It'll have a higher ending point.
It'll stretch it this way, yeah. It'll point towards a higher value. The higher Vs is, the higher it's going to go. If I change Vs, it stretches the function vertically. If I change the value of S, it stretches the function horizontally. The larger the S value, the longer it's going to take to reach equilibrium. And actually, it's the larger the tau value here, not S. The smaller the value of S is, the longer it's going to take. The larger the value of tau, the longer it's going to take. okay? So that's interesting. What that means here is in order to make this value smaller, R1 and C1 have to be larger values. If you have a higher capacitance, it means you have more charges that can be stored on the capacitor, okay? So having more charges being able to store it on the capacitor means it takes longer to fully charge the capacitor. That makes sense. Similarly, having a higher resistance means you have less current flowing through the system. Resistance decreases current. So if you limit the amount of current that's going into the capacitor, it's going to take longer for the capacitor to charge. Increasing both the resistance and the capacitance will stretch this out to the right, and we'll just simply make it take longer. Okay? That's going to be one of your quiz questions for next week. All right. Okay. Let's go ahead and take a 10-minute break. Come back here 9:38. We'll keep going.